Okay, we stopped with the root locus, right? And we're going to finish that topic today, at least for, yeah, no, we're going to finish it today. I hope so. We get through it. So, big picture. Root locus is a plot which shows you where you can place your closed loop poles at, right? If you're not happy where you can place it at, we need to do something, right? We need to change the root locus curves. And this is the part we're talking about now. So far, we realized we can check points, which we like to have. If they're on our root locus curve, and this is the famous. This is the famous angle criterion, right? And we figured at the end of the last lecture, after some mathematical derivation, this is actually comes down to pure angle computations. And if the angle turns out to be 180, we know we can get a proportional real feedback gain out of that, and then we basically can compute the gain. And this was actually where we stopped. So we said, okay, this is the angle criterion. We only need to sum up all the angles, and we're going to do a couple of more examples on that, and then you can jump right into the examples on our Moodle course. Okay, and then we said, okay, what happens with the gain? Well, then if we do the same thing we've done before with the gain, we actually realize, okay, we also can calculate directly the gain we need from our G of S of our system, right? We don't need anything else. And also there are some good news. If you want to compute the gain of a transfer function to a certain point, so SA in this case is the point which we desired our closed loop poles to be. This is the very, not so nice actually equation. You need to, but what this equation says, you basically need only to take all the distances from your zeros to this point and all the pole and divide it through all the distances multiplied together by the poles to your point. So what that means is, for this very simple example, you only need to calculate the distance from this one pole to the point. And again, this is pure. You can actually take a ruler and measure it. Most of the time, you probably would want to prefer doing that with a simple Pythagoras, right? Because you know the coordinates of this point here, you know the coordinates of this guy here, because this is your system, and then you can do the computation to get out this distance. And based on these distances, you actually can compute your gain you need. There's one thing we need to consider, and this is what usually or often happens or students forget. Actually, last semester nobody forgot it. Nearly nobody forgot it in exam, because I think because I was telling it a couple of times. So the problem is that the issue is that we also need to consider this gain k tilde of our system. And remember, when we have our system in the pole zero form, let me write it down, why this is actually the case. So let's say we have a system which is S plus 1, S plus 2, S plus 10 as a 0, and we have 10 here. So when you're drawing that pole zero map of this guy, real and imaginary, right? So you take on the first pole, okay, minus 1. Take on the second pole, minus 2. Then you take the 0, minus 10. You have the 0 here. And now you say, okay, I want to do the computation if I can reach this point here. Right? Let's say this here. So what you're doing is, and let's say you're reaching it, and now what this criterion here, or not criterion, what this strategy says here, okay, we need to compute all the distances here, right? All the distances from each and every pole and 0. Okay, so now let's take a look what we have done. We have considered that pole, we have considered that pole, we have considered that 0. However, when you look at the pole 0 map, this k tilde is missing here, right? So all the information does, when you do this computation here, this your gain k tilde is missing in that equation, and this is why you also have to consider that for the computation of your final controller gain. You don't only need to divide do 1 over this guy here, the distances of what you directly get out of your pole zero plot. You also need to consider this pure gain here, right? Because this gain does not show up in the pole zero map, right? So we must not forget this guy. So as a recapture, what this k tilde is, this k tilde is if you have your transfer function in the pole zero form. And let me tell you this. I know we have pole zero form, we have time constant form. For this strategy, for the root locus, you should always prefer the pole zero form. Why? Well, because the root locus curves are drawn in the pole zero map, right? So it definitely makes sense to have our system also in the pole zero form, because these guys here, this P1 and mu, they directly show up in here, right? So this guy is -1. And actually, I'm realizing they should all be minus here, but never mind. They show up all here, so it does not make really sense to actually work with the time constant form at this stage, right? So really consider always having the pole zero form, and this is why actually I introduced this gain k tilde, which is not your static gain, because for the static gain you also need to consider all these guys, right? So this is why I explicitly introduced it when we talked about the transfer function, this k tilde here. It's basically all the rest of the gains which are not covered by all the poles and zeros. It's the value to get the static gain right, so to say. Remember when we switched around between pole zero form, polynomial form, and time constant form, this was the guy always to be changed, that the static gain finally does not change. This is why I think I talked about it a couple of times, and now here we explicitly need it because we should not forget it. But we will have an example on that immediately. Okay. Yeah. This is a small fix. There should be minus signs here, right? So actually I can fix this now, because if this guy here is at -1, it should be +1 here. So you need to have -1. This obviously then is a plus, so you have to go S minus P1. Okay, this was a sloppy mistake from my side. Sorry for that. Well, I fixed that. Okay. So let's summarize the procedure which we derived in the last hour, let's say. Okay, first we need to select the point which we are interested to place our poles at, right? And for that, we want to determine a proportional gain. But we only can compute the proportional gain of the controller if this point actually lies on the root locus. So let's check. So we calculate the angle criterion, right? So we calculate to that point all the angles of our system. And here, remember, we made our lives a lot easier because now we only have to take the system and measure the angles to that point. We never ever calculate this KP and look if it's real or it's complex, right? This comes after. This angle criterion is purely looking at the angles of the system to that point. That's it. In case the angle is minus 180 degrees or 180 degrees and so on, so pi plus 2 pi times n, then we actually know that the gain is real, and then we actually calculate our feedback gain, our proportional feedback set. If this guy is not 180 plus minus 2 pi n, then it does not make sense, because then we need to think of adding some dynamics. Yeah, and finally, we calculate the magnitude to get this. So this is the evaluation of the criterion, and then we finally can compute the gain. So one more question is now, I'm always telling you, you have some desired points in mind, right? In the road locus, on the pole zero map, where you want to place your poles at. But this actually assumes that you know where you want to place your poles at, and there is no general solution. But I will show you a couple of areas which are a good idea. You should at this point already know, never place it on the right half plane, because then we have an unstable system. So your goal should never be placing a pole in the right half plane in the closed loop, because then your closed loop will be unstable. So the left half plane is a good idea. And this is already the very basic control design. But we will come to that. Before that, I actually want to do 3 calculations example on this angle criterion. Actually get a little bit of practice how you would do this, right? So let's stick for the angle criterion for the moment and take our beloved system here, which is this PD2 system. And we have covered this a couple of times, right? We have the poles at minus 0.8 plus minus 3.9. We have a static gain of 0.5, right? 4/16. This guy here, we need that explicitly later on. It's 4, right? Because all of this we cover by the pole zero map. However, this gain, this K tilde, we don't. And if you do the midnight formula and calculate gain and damping, or do a comparing of the coefficients, you get an eigenfrequency of 4, right? Square root of this guy here. And you have a damping of 0.2. So nothing new here. Okay, but now let's say we want to design a controller, and this controller should be a proportional controller. And for that, we will have 3 scenarios where we have points in mind, right? So I give you now 3 points in the pole zero map where it might be a good idea to place the poles at. And then we're going to check if we can reach these points in a closed loop by the angle criterion. So this is what we're going to do. So let's consider design example number 1 is going to be, we want to keep the natural frequency constant. So we want to stay at omega 0.4 and just increase the damping. Well, what does that mean in terms of a time response? Well, we have less oscillation. So this is usually a really good idea what you want in practice. Think of an aircraft wing, and this is actually what you do. When the aircraft wing is made of nowadays of carbon fiber, they tend to kind of oscillate. They have eigenmodes, right? And there in the A350, for example, there are active strategies to increase only the damping, right? That the wing is not able to oscillate that much anymore. And this happens actually with pure control. So it's an artificial system. You don't put any mass in there. It's really controlled actively. The damping is increased. Okay, so this would be the first example. So we don't change the speed, we just want to change the damping. Okay. Next thing, we want to increase the imaginary part of the poles, right? So this guy, so we want to move these poles further to the outside. Thereby, we actually will decrease the damping, but we will increase the frequency. To be fair, practically this would not be what you want to do, right? Because if the damping is 0.2, you don't want to make it any lower, because it will add oscillation to your closed loop. So, but we know that this guy is on the closed loop, and this is on the root locus, and this is why I have this example in there. Okay, and finally, we want to increase the damping to be larger than 1. With half the natural frequency, right? So we want to increase the damping further, not 0.7. We know when we increase it further, we will get a pole somewhere. We will have basically 2 poles, and the slower one will dominate our response. And for that one, we want to have an eigenfrequency which is half the natural one, right? Okay. So let's take a look how these 2 constraints and or these 3 constraints or design examples and our system looks in the pole zero map. Okay, so if you look here, this is our system, right? These are the poles of our system. These 2, it's a PD2. The first design example, we said we want to increase the damping from 0.2 to 0.7. And keep the natural frequency constant. So the natural frequency, you see these circles here, right? These are the natural frequency, and our system is exactly at 4. So we want to move along this circle until we hit 0.7, and the lines here are the damping lines. So our design point to increase the damping to 0.7 would be exactly this one. This is where we want to end up the poles to be. And see, these are the poles of the system at this point. So we want to move them left and down. The second example was we want to increase just the natural frequency or the imaginary part. So we want to move this guy up and don't change the real part, right? So for example, if we want to do that, we want to increase this guy to 5.1, for example, and leave the real part constant, right? And finally, we want to move that guy, increase the damping further, and we know that this guy moves down, and probably we want to have some pole here at -2, because here this guy will be slower. We'll have a position of -2 means an eigenfrequency of, well, actually a time constant then of 0.5. So actually making our systems a little bit slower. Okay. At this point, you probably realize that only one of these points, namely B, is on our root locus curve, right? So what you could do is plot the root locus curve for our PD2 system at this stage, and you know that, that actually the root locus curve looks like this, right? Same as before. We've covered it a couple of times now. So, but it's actually pretty similar than the introduction examples where we looked for the gain, how it looks like, but this time we don't compute the gain. We do the same thing via the angle criterion, right? I'm going to show you that. Okay, so we compute for all these points the angle criterion and see what's happened, and we'll see what will happen. So, okay, let's start with point A, because this, I think, is probably the most challenging one, right? So what we need to do now is for point 2, let's do a little bit with the colors. Let's get rid of this. Let's go point A with magenta. We need to compute the angles from here, from this guy and from this guy, right? So we basically need to compute this angle and we need to compute this angle. And this is what is shown on the next page. Okay, actually I shouldn't have needed to draw it, because here it's anyway. So this is the first angle for the angle criterion. And this guy, basically, what can we say about this guy? This is definitely going to be more than 180 degrees, right? So it's definitely more than pi, right? Okay, so we can take pi, 180 degrees, and add something, right? And this something is the interesting part. Well, this something basically comes from the tangents computation of this triangle, right? So tangents is this side here, and this side is nothing but take the imaginary part of this guy and subtract the imaginary part of this guy, right? Then you have this delta here. Okay, this is your Gegenkathete. I don't know what this is in English. Okay, never mind. Okay, and then we need to divide through this part here, this length. And this length is basically the real part of P1, right? Minus the real part of P. And then we get to that angle. And this angle is roughly 208 degrees. Okay, so take care of the sign here, right? Because they are both negative, you need to switch them over, right? So the real part P1 is less negative than this one. That's why I changed I changed the numbering here. So it's basically because this guy is less negative than this, so you need to take care of the sign. Anyway, this guy is about 208 degrees. Okay, second angle, it's roughly pi over 2, so pi over 2, 90 degrees plus something, okay? And this something is interesting. So with pi over 2 over something is simply, okay, for, again, you can do the tangents computation here, because you basically need that something here, call it x, right? It's again, this part is the same thing as above, right? This here is the same. You can put in P1 or P2, but because they have the same real part, because they are conjugate complex. And then you need to look for the imaginary part, which is basically this guy here plus this guy here, right? What means that you take the imaginary part of A and subtract the imaginary part of P2, because the imaginary part of P2 is negative, so you basically add the imaginary part of P1, right? Okay, this angle here is roughly 106 degrees, and this is about right if you look here, right? 106. Okay, so we computed the angles, and now we can evaluate the criterion. So we need now to make them negative. If you go back to the criterion, let me jump back. This is a couple of slides back. So where is the criterion? On 74, I think, yes. So you add the angles from the zeros and you subtract the sum of the poles. We only have 2 poles, right? So they're going to turn out negative. So this sign here is negative. So we have, sorry for that, negative. Add these 2 and make them negative. And we realize this guy is not 180 degrees, right? It's closer actually to 2 pi, so to 360 degrees. It's definitely not going to be on our root locus curve, right? So, but yeah, we know that from the root locus, from the simple root locus curve of this PD2. But here is the validation of that, or the confirmation that this point is not on a root locus curve based on the angle criterion. Okay, so yeah, we cannot reach it with positive or negative gain, right? I just said positive gain, but obviously because if this guy would be minus 2 pi, we would have reached it with negative gain, but it's not the case. So we cannot reach this one. So please stick, remember that examples, because we're going to design a controller for this guy to actually reach point A later on. Okay, let's go to point B. Okay, let's go back to the big picture here. Here is point B. Where's it? So here's point B. Right, let's do a different color here. Okay, here this point B is basically just straight up our point. So this is kind of exactly 90 degrees, right? And from here to point B is also 90 degrees, right? Because why it's exactly 90? Well, we have the same real part, right? Minus 0.8, minus 0.8. So it must be exactly 90 degrees from the horizontal. Okay, can use that. So we know that the angle from our first pole is the same thing as the angle from our second pole, and it's pi over 2. So we calculate the angle criterion of GB. Well, it's just the sum of all our angles. They go in negative, so it's minus pi, right? Clearly, this is 100 or minus 180 degrees. This is okay. This point is on the root locus curve, and we can reach that point with a positive feedback. Okay, perfect. So what did we say? If it turns out that we can reach it, well, the next step is to calculate the gain we want to have, right? And there's where the magnitude or the gain criterion comes into play. And remember, this is the simple formula where we all need to calculate the distances. So actually I have the formula here. So the corresponding magnitude of the gain, we need to basically take that k tilde and the distance from our system to that point and invert it. So if you fill that, I think it might happen that in your script there's still a k0. It's not wrong in that example, but it's actually because the inverse of k, I think of k tilde is 0.25. So yeah, but the correct one would be k tilde inverse here. Okay, and this guy is simply what we had a couple of slides back, right? So the magnitude criterion. I will jump back to that. This is exactly this guy here. And as we needed to invert, see there's this -1 here to the power of -1, we actually can turn this around, right? We can write the distances to the poles over the distances to the zeros because this -1 here. Okay, go back. This is where we are. Okay, so let's talk about this. This K tilde is is actually 4, right? You have the system here. K tilde is 4. So we inverted, it's 0.25, so it's the same thing as K0, but this is really just a coincidence, right? Setting up a problem of the problem. So K tilde inverse is 0.25, and then we need the distances between the point and the pole. Well, this is not too hard, right? So take the first point. This guy has a distance here of, the pole is 3.92, and this distance here is simply then 5.1 minus 3.92, right? And this should be nothing but 1.18, yes, okay? And for the second pole, we need to compute all over the way from here to here. So it's basically 5.1 plus 3.92, right? And this is roughly 9.02 or something. Okay. It's really pure measuring out the distances, right? And they go in here. And now we know with the gain of 2.6 in the controller, we exactly reach our desired point B. Okay. Finally, point C. Let's go back to this, where our point C, where we see that. I actually, again, get rid of this to be able to focus on point C. Let's see what colors do we have left. Blue, maybe. Okay, so now we need to compute again the angles from here to our point C. It's definitely going to be pi plus something, right? And this guy here is going to be pi over 2 plus something, right? So it's definitely more than 90 degrees. Okay. I encourage you to do this as an exercise on your own. What the result is that your first angle is 1.41 pi, so it's about 245 degrees, and the second angle is 0.59 pi, so about, if you want to really measure it out, 106 degrees. So one thing probably which you really need to take care, because I figured out that last semester that somebody did, you actually can measure it with a ruler, right? But then you need to be careful that your axes are equally scaled, right? So it needs basically to have 1 centimeter should on the x-axis and on the y-axis be the same distance. So because the pole zero plot is often kind of scaled on the x and the y-axis. And it is, if this is the case, you cannot simply measure out and use the tangents, because there's an inherent scaling in the plot then, right? So if you really want to measure it. Yeah, if you have an example in the exam where you can measure it, I will explicitly say that, and it obviously will be rightly scaled for you, right? So, but yeah, be careful here. Okay, so if you sum them up, so if you do the sum of the angles of our system to C, you will realize that this guy is immediately 2 pi, and which is equal 0, right? Because it's just 360 degrees shifted. Okay, what does that mean now? The point is not on our root locus curve for positive feedback, but with a negative one. Now this is exactly the case where you need to change the sign. So what happens is you still can compute your gain with the formula. The distances are 4.1 each. This guy does not change, right? And you come up with a gain of 4. However, as we know now, we have a phase shift of, or an angle shift basically, of 180 degrees. We need to multiply this guy by -1. So the gain, what you need to implement into your controller to reach that point is simply -4, right? Okay. So that's it actually for the angle criterion. We now basically moved from that point where we needed, and it took quite a long time, we moved from the point where we actually had to evaluate the characteristic equation to understand if a point is on a root locus plot or not, to a point where we just need to compute some angles, right? And this understanding of the angle now turns over to the control design pretty easily, because, and I will come to that after. Now let's talk about this, because we're in the middle of it. So when you say, oh, so this is the control design strategy. My point here I want to reach is not on the root locus curve, because my angle is not 180, but it's 200. Okay, so this is not a simple yes or no. Yes, it is a simple yes or no statement, right? Because we know it's not on the curve. But when you now ask yourself, what do I need to do to put it on the root locus curve? Well, we need to find somewhere 20 degrees of angle, if it's 200 degrees, which we can subtract to get to 180 degrees. So this is actually not only a yes and no, this is already a quantitative information you have there. We are missing 20 degrees for that example I just mentioned, and because if it's going to be 180, then we know it's on there. And now the final step is, okay, I'm missing something, or I need to add something, and we know how the angle criteria is built up, right? Zeros add something, and poles add something, right? So we can actually now think of, okay, we can add poles and zeros to change this angle criterion, and we place the pole and zeros in the diagram to a certain point that we exactly get the missing angle, right? In this case, 20 degrees. Okay, I hope this was not too fast. If so, we will come to that. What I want to discuss next is a big picture on the design criterion, and then finally, I promised you, I always saying some points in the closed loop in mind in the pole zero map. So what does that mean? We will discuss a couple of areas in the pole zero map which are probably a good idea to place your poles at, right? Okay, for that angle criterion, there's actually also, I did mention it, a MATLAB file now, which I kind of coded up. So if you have any system, you basically can run this file and it checks your system to a specific point, right? For example, this P is actually a DT2 system, and this point, can you reach that? And what the code does, it basically tells you yes or no, it's on the root locus or not. So it does basically a full evaluation of the angle criterion, and if it is fulfilled, it also computes it the gain. So for those of you who like programming, or actually who just want to check your results on the examples, I really encourage you to directly use these folders, because these files, because thereby you not only learn how the angle criterion works, which you need anyway, but you also get to know some coding, right? And you can check your results on your own, right? Maybe you find an error in the code, but I think it's after 3 semesters, it's well developed, so hopefully not. Okay, finally, let's go to the to our storyline. Yeah, exactly. So we have the methodology how to check a point, and now we usually have some point in mind. And this, what we have in mind, we're going to discuss shortly. That you actually in practice have a good idea where you want to put your poles at. Okay, so finally, this was what was all the work for. We come to the actual control design using root locus. So what we actually want to do, instead of just checking if something is on our root locus curve, we want to actively modify those curves now. So, because usually pure proportional feedback is not good enough. But what we know is that if we add zeros, right, to our system, they're going to pull our root locus curve to these zeros. Why? Because the root locus curves will end in those zeros. And if our controller has zeros, like a PID controller, we can use those zeros to kind of pull our root locus curve into that direction. We also know that zeros themselves add some positive angle, while poles add negative, right? So depending on where we are with our angle criterion, we actually can use this fact that by zeros we are adding some angle, and by poles we are subtracting some angle. We can get to the point to make the criterion finally to 180. If it's at 200, we know subtracting 20 would be good to get to 180. So why not placing a pole? Or alternatively, we can, if you want to add something to get to 540, you need to add a lot. So yeah, we keep with the subtracting. But yeah, so we can use those ideas of the angle criterion to add these poles and zeros to a certain location to finally meet the angle criterion. This is the whole idea of a root locus design using pole zero map on paper. Okay, so lay out the strategy. First, this is really always the first point I recommend you to think about. You need to decide if you want to go have steady state accuracy or not, right? If so, you add the integrator to your system. And remember here, this is what we started the day with, where we said, yes, we always can add dynamics to our, and still use the root locus plots. We just need to stick all the dynamics to our system, to our augmented system, and then look for the proportional feedback. And usually you will not add an integrator because you need or less angle in the criterion. You add the integrator because you want to have steady state accuracy. So this is a point you as engineer need to get clear right at the beginning, right? Okay, if so, you want to select the desired point in the pole zero map or plane, right? So you really want to say, I want to place my closed loop poles there or there or there. How you select that spot, we're going to discuss immediately. And then, if the angle criterion is not met, and this will usually be the case, then you need to introduce dynamics in the controller. So you need to add zeros and poles to finally meet the angle criterion for that desired point. And then if this happens, then you calculate the gain, right? And obviously, you should realize that this is a little bit an iterative process, right? Although all the examples we are doing in class might be made up in a way that you immediately can get to the result. In practice, it's usually you have some iterations, right? Okay, so finally, I want to discuss with you what are good areas to place your poles at, or not what are good areas, but what are different areas telling us about the system? How can we turn design criterions into pole locations? Because this is a thing usually which is completely forgotten, right? Okay, we're going to place the pole somewhere, but why, right? So this is, I think, a crucial part for every control engineer. So where does it make sense to place your dominant poles at? Well, the most principal design requirement for every control system is that you need a stable system. It does really not make sense to have a closed loop system which is unstable. This is really the basic design criterion in control. Your closed loop needs to be stable, right? So never ever put your closed loop poles, please, in the right half plane. because this system is not usable. That would mean you switch on your espresso machine and it would cook up until it breaks. So does not make sense, right? Your aircraft for a pilot will not be flyable, it will crash. Don't ever design an unstable system. So this is a very basic design criterion. If you don't fulfill that, it doesn't make sense to talk about something else. The issue with that is that you can say, okay, this here will be a stable system, right? Or this here. However, it is problematic because it's so close to the unstable region. This is why we are usually, force a lower bound on the damping requirement. And I told you the damping requirement, or the damping in the pole zero map, are these constant lines here. What you usually do in practice is to say, we want to have a minimum damping of 0.7. We want to have a minimum damping of 0.9, something like this. For example, for aircraft, it's clearly, I think, 0.6 or something. You should not have an aircraft with a damping lower than 0.6, where 0.71 is the optimal, which we discussed, right? So what you also have is, in that way, you have basically an area which moves you away from this unstable region. Obviously, here is still a region which is close to the unstable region. However, usually especially when you have mechanical problems, they're all showing up here, and you want to increase and enforce a minimum damping, right? So this is definitely going to be a better area than this first minimum criteria you want to have, right? Okay. Often what you're going to say is, okay, I want to have a minimum on my decay time, right? And remember, what does a pole have? A pole always has a real part, right? So P1, 2, not I1, 2 has a real part and an imaginary part. And this real part shows up in your exponential function, right? So it has minus RE times T, and if it's oscillating, it has some contribution from the sine wave from the imaginary part as well. But these guys show up in the imaginary part of your time in the exponential of your time response. So if you want to say, I want to make this faster than, I don't know, 1 second, then you would place this guy to 1, right? So all this here would be too slow for your design criteria. So, and this is actually, these two guys are pretty important, especially when you work in flight control, because they two are kind of often fused to one criterion. And I've tried to sketch that out. So if you kind of take this one and add this one here, you basically come to something which looks like this, right? So this is also a no-go, and here it's going to be fine, right? So in practice, you will find often something, I don't know how you call this, geometric figure, which looks like this. So this could be an area which is good because it stays away from the unstable part. It has a minimum damping, and it's fast enough. So you have a good criteria also for your exponential decay time, basically. Okay. If you want to talk about the damped frequency, right? So your omega E is basically here and here, right? You can think of lower and upper bounds on this damped frequency. Remember when we talked about the PD2 system, this damped frequency basically resulted from the period of the period of your time response, and this omega E was nothing but TP to the -1 times 2 pi, right? To be fair, it's not often done, right? What's more often done is to put an upper or lower bound on the eigenfrequency, on the natural frequency itself, right? As I told you, these circles here, for example, here would be an omega 0 of 3. If you want to have them lower, you go for this area. If you want to have them bigger than 3, you want to have this here, right? And this is all what I got for the criterion, right? So here really is, yeah, your engineering knowledge comes into play. You say, okay, my spring mass damper is, or my damper in my, let's say you have a car and you have like a damper system, and this is kind of too lightly damped, you increase the damping, or it's too slow, you need to increase the eigenfrequency, or it's too fast, you decrease it. This is how you would tackle such problems, thinking of damping, eigenfrequency, and decay time. That's basically it. And always have in your mind stability. Stability is really like the key what you always need. So you never ever need to think about the right half plane, right? So always stick to the left half plane, and then you can think of points where you want to place your closed loop poles at. I hope this gave you some ideas how to tackle that problem. Okay, so finally we want to do a design example, right? And there you see how we actually doing a design based on a Locus on paper, right? And we're going to go back to our example on this PD2 system. Okay, here nothing new. It's this PD2 system, eigenfrequency of 4, damping of 0.2. This K tilde is 4, the static gain is 0.25, and we've got our poles. And what we said, this actually this design point A did not change, right? This is the same as before. So we said, okay, we just want to increase the damping coming from here, moving along that, it's not a circle now, along that circle to a point where we reach a damping of 0.7. Okay? So, now I lost my point. Okay, no, we want to increase it to 0.6 at this point. This is exactly this line right here. Okay, if you do the angle criterion, right? We said a couple of slides ago, the angle criterion resulted in something like was roughly, I think, 0.7 pi. And we can check back. I'm going to check back with if this is the right case. Oh no, okay, there the angle criterion was minus 1.75, but we wanted to place the damping at 0.7. Okay, so it's not totally the same. Now we want to place the damping at 0.6, and the angle criterion gives us 0.7 pi. So if you put that in your calculator, 1.7, not 0.7, kidding. It's roughly 306 degrees, right? So if you want to have it in degrees. So this is obviously not pi or minus pi, and actually the angle criterion gives you a negative, right? So this is smaller than minus pi, which we would require to actually have this guy on this point on our root locus curve. You should know it's again a PD2 system, so our root locus curve simply looks like this, right? We clearly cannot reach A by simple proportional feedback. This is confirmed here by the angle criterion. But now still, this is what I try to emphasize. The angle criterion basically is a yes and no. No, it's not on our root locus curve, but we can use the angle criterion a little bit more. The angle criterion tells us we are basically missing 0.7 pi of angle, right? Because if we would have 0.7 pi more, the angle criterion would be exactly minus pi. So where do we get this 0.7 from? Well, now we know that if we place a 0 somewhere in our system, we will get a little bit more angle from that 0. If you look at the angle criterion, the 0 adds positive angle in here. So what we can get out from it, we need to place somewhere a 0, which adds us 0.7 pi in angle. And if you want to have it not in pi, we need 126 degrees in angle, okay? Which this 0 should contribute. So we can say, okay, we want to add a 0 in our controller, which adds that angle, so that our root locus curve finally goes through that point A. If we achieve that, we then can compute the gain, and we're done. Okay, so instead of a pure proportional controller, we're going to add a D term. So we're going to say, okay, our controller needs to look like we have a gain, PD, and we have a 0. So the question is now, what's that gain here and what's that 0 here? And we can get out this 0 by actually knowing that we need, what did I say, 126 degrees from that 0, okay? Okay, and with this is a pure graphical information we have here, okay? And now we just do a little bit of Pythagoras computation and tangents computation, I think. Okay, so let's see what we have. This is a picture now. We decided for the 0, right? Because we said, okay, the 0 will add us some angle in the angle criterion, and we are missing this 126. So the question is where to put the 0. So the first thing is, well, what happens if I place it here? Right? So if I place it here, the angle which I'm getting is smaller than 90 degrees, right? Because if I move further to this direction, it will actually get smaller. And if I put it here, it's exactly going to be 90 degrees. So this is not a good idea. Why? Because we want to have 126 degrees. So we need more than 90 degrees. So it's definitely going to be a good idea to put it on the right side of our point A, because we need more than 90 degrees. Okay, and now the question is where to put it here exactly. And for that, we can use geometry, right? Okay, so 126 degrees are nothing but pi over 2, so 90 degrees plus something, right? And this something here is interesting. We already covered this 90 degrees because we placed it right off our point A. So these are already 90 degrees, right? So we have them. So the question is now, how do we get this 36 degrees out? Okay, but we can compute that, right? Okay, how do we compute it? Well, we know that, actually there's a line missing. We know that this distance here is the distance where we want to put our 0 away on the x-axis from A, right? But we don't know that. But what we know is, let's see, change the color. We know this guy here, right? This distance is given by our point A, and we defined it point A. So this is clear. And what we also know is this angle here, right? Roughly 36 degrees. Okay, so we can use a tangent. So what's the tangent of that angle here, of the delta? Is nothing but C over the imaginary part of A, right? Okay, so we can transform this after, or we can calculate C out of this. So we take the imaginary part of A multiplied by the tangents, and we get out a distance of 2.4. So we need to place the distance. We need to place the 0 to a value of 2.4 from that point. Okay, so where is that? We simply take the real part of A, and I'm going to cheat because I'm going to look back on the last slide. Minus 2.4. Okay, very well constructed problem. So this guy here is minus 2.4. We add 2.4, and it's going to be 0. So we need to place a 0 at 0, a 0 at the origin. So this 0 needs to be placed here. Okay. What happens if we place the 0 exactly at 0? We're gonna add exactly the angle we need, and point A will be on our root locus curve. That's all we need, right? Okay. Okay. So we have a controller, a PD controller, which has two free parameters, the gain and the zero. We use the gain, we use the zero, it's going to get a little bit late. We use the zero to meet our angle criterion to make the root locus curve through that, make that root locus curve go through that point A. Now we have achieved this, we have that location, and the second free parameter is the gain, and we compute that gain because we still need to have a gain value to exactly hit that point, right? It doesn't help that the curve goes through, we also need the gain value. Okay. Yeah, so our new system now, and this is really important. Well, this is important here. Our new system is, and this is what I did in the morning, right? If you want to remember that, we have our system G of S, and we have, let's change the color. We have the controller, which is set up of KP, and a zero. In our case, the zero is at zero, so okay, we can write it like this. So this is going to be, the blue one is going to be our controller. But for the computation of the root locus curve, we need to see this as new augmented plant. Let's call it G tilde. Okay. Okay, so why is this important? Because this is when you do the examples later on our Moodle course, you will see that it's easy to forget that part, right? If you would do the re-evaluation of the angle criteria, you need to consider that zero, obviously, otherwise it doesn't fit, right? But you also need to take that zero into account for the computation of the gain. Please, really don't forget these zeros and poles you're introducing into your controller. Let's say if I tell you, please design a controller which has an integral part, you also need to take that integrator and consider it for the computation of the gain, right? So please really don't forget it. Okay, so the gain is nothing but, okay, we need to invert the distances, and I'm doing this pretty quickly now. You can actually do the computation at home as an exercises. What you need to do is simply, you need to compute these distances, right? This is now I got lost. This is the distance of the first pole, this is the distance of the second pole, and then you need to compute the distance of this zero here, which comes from the controller. And if you do that, it's simple Pythagoras, right? You get to values of 1.7573, and this is which comes from our zero. Plug everything in and you get a gain of 0.8 out of it. So now we have a controller, and our PD controller R of S is nothing but 0.8 times S, right? Because it's S plus 0 and this is 0.8 S. And this controller, it's actually not a PD controller anymore, it's a pure D controller, which I told you is not really a controller, but it's actually pretty nice for that examples. And this actually is what, it has a mechanical background why it's only a D controller. What is a D controller doing? It's basically taking your output of our PD2 of our spring mass damper system. The output is the position. The D controller makes of that position a velocity and feeds the velocity back, and the pure velocity feedback will only increase the damping and not the ion frequency. Okay, this is what this example actually confirms. Okay, not so good. But this is the link to the very same MATLAB file as we've had here. So you can actually see this is our controller S, and you can do the computation. And if you scroll down, this is basically the second part. You see that with a pure differentiator, now we actually reach that point, right? And you can compute the gain, and it should be somewhere here. Well, this is 4 because, yeah, it's a different, no, here it's 0.8, right? So it's okay. So the gain which we get out in the lecture is also confirmed here. Resulting controller is 0.8. Okay. So that's basically it. So while it took us a long time to get the understanding of it, the actually control design with the root locus is actually pretty, yeah, it's just doing some angle computation. Obviously, doing angle computation on the one hand is easy, but it's easy to make sloppy mistakes. So really, please be careful. The nice thing about this methodology is that you, yeah, if you practice it a little bit, it's always the same scheme, right? Okay. There are, I think, 3 or 4 slides left for discussion, and then I'll show you the example, and then we're going to probably close the lecture for today already. Okay. So, yeah, this PID controller is not realizable, right? Because it's not a PD, it's actually a pure D controller, and we figured it requires some to realize it. It requires an additional pole. It requires this parasitic delay, right? So what happens when we add a parasitic delay? We add a pole in our system, and that pole kind of again gives us some negative angle. So what will happen is no matter where we place that pole, it's gonna drag our root locus curve away from that point A, right? This is actually how can we avoid this? Okay, the result is now we need a pure differential controller. So for that we need a pole, so we can do an iteration around, right? We can now add this pole and do this calculation again, and you will see that the 0 then moves a little bit to the, should move a little bit to the right, so we're actually getting to place the 0 in the right half plane a little bit, just to compensate for that pole, okay? But yeah, in practice you need to be aware of that, making this pole realizable actually adds you a little bit of angle change. This is what you see here, and you would need to relocate this 0 again. So what you see here, the green line is what we designed it for, right? Now I'm adding a PDT1 controller. It's actually a DT1 controller with a pole at -20. So the pole is somewhere out here. And this kind of drags our curve a little bit away from that point. Point A was exactly here, right? This is A. And as we're adding another pole, we are having a little bit, we are again not meeting the angle criteria. So if that turns out, we need to relocate it. So this is why I said this whole process is a little bit of an iterative thing. Okay. So what I want to bring up at the end is really, again, this integral action, right? So you will never, most of the time, you will not add an integrator because you want to add some, you want to get some angle away from your criterion, because clearly when you add the integrator, it changes your angle criterion, right? Pure integrators are added in your controller for steady state accuracy. So it definitely makes also sense to add them at the beginning and think about it. Do you need them? Do you not need them, right? So put the integrators in first. As I said, they add negative phase or angle, whatever you want to call it. And this is why we are actually often using a PD controller. So there's a question in the chat. Oh, I need to translate on the fly. Ich lese mal auf Deutsch. Sollen wir immer vom Minus-Pi-Winkel ausgehen zur Auslegung oder können wir minus 2Pi auch arbeiten? Wenn beim letzten Beispiel sind wir schon davon ausgegangen, dass wir minus Pi brauchen. Wenn ich aber minus 2 brauchen sollte, sollte ich einen Pol mit minus 0,3 Pi einfügen. Beim letzten Beispiel, last example, it's probably this one here, right? So let's think about, you could add 0.3, you would add a pole This pole would be you would have negative phase. Yeah. So the problem is, yes, I would recommend going with this minus pi, because what would happen is, if you would clearly need to add a pole to make the gain more negative, right? To make the phase more negative. So you would need 0.3 times 180 is about 50 degrees. So 50 degrees is you would add a pole here, right? This would be roughly 55 degrees, right? So now, however, you would need to go with positive feedback, right? And remember now, the root locus curve will change with positive feedback. So what will happen is, then, okay, now I need to think, these guys will go here. We will have two poles going to infinity. Now I have to think in reverse, right? Because this guy, yeah, what's going to happen is following, I think. They're all going to go still to infinity, right? This guy will go here, this will go here, they're going to meet here, and this point is going to go this way. So, yeah, I hope you see that's probably not a good idea. If you decide to go that way, and if I say, I will probably tell you in the example, please design a controller and make sure that the closed loop is stable, right? And I'm quite sure this one is not going to be stable, because you can meet that point, but as you have 3 poles, right? One is going to move to the right hand side. So what you're always going to do is, when you do, if you change to the 2 pi or minus 2 pi or minus 4 pi, you will do a destabilization of the loop, and this is actually what's happening here. So I would encourage you to always go to the minus pi, plus pi, or 3 pi, 5 pi, or so on, right? Because most of the time, definitely the constructed problems for the exam, they will be that you end up with a stable loop, And this is actually a very good question, because this already shows you the limitations of the root locus curve, or the root locus thing, because we are always thinking only of one point in the map, and one point means we can place one pole there, but it does not tell us where the others go, right? So the result is here that these root locus curves, when you do it on paper, work pretty well for low order examples. When you have 100 poles, they're gonna get a nightmare, and we will have a different method for that. So bottom line, please, I would really try to not destabilize the loop, and always go with negative feedback, and thereby stick to minus 180, minus 540, and so on. Yeah, I hope this was kind of clear what I kind of explained. Okay, let's go back to the integrators. Yeah, an integrator basically adds, again, negative phase, right? Poles always make your system slower. So this is kind of actually related to this question. Whenever you can, try to add zeros, because zeros make your system faster, more stable. And so whenever you add poles, you add lagginess, right? A pole is always a lag, and lag is usually not a good idea for control systems. You make your system slower, you make it less damped, and so on, right? So always, actually, you can take it as a rule, always try to add zeros to add an angle and not make it even worse, right? Yeah. Again, and this is the interpretation also what we have discussed already. When you have a system, let's say if you have an ID2 system, right, where you already have an integrator, we said, this is kind of problematic. Sometimes, in this case, it's really actually hard to add another integrator in our controller because we already have one. This whole methodology actually gives you another interpretation of that, because an integrator adds already a lot of negative angle. So if you add another one, you have even more negative angle, and you will need to compensate this with another 0 to make the system just faster. The more poles you add in your system, the more lag you add. It's, yeah, you want to avoid that. But actually a very good question, so thanks for asking that one. Okay, that's basically it. Now, to be fair, controllers nowadays are rarely, they are rarely designed on paper anymore. The root locus method was a pretty good method for the paper, right? When we didn't have any computers, right? Nowadays, we are using CAD tools, right? We just run MATLAB and we immediately can add poles and zeros where we want it to. Still, we need the crucial understanding that a pole is not so good because we are losing angle, and with a 0 we are winning angles, right? So a 0 is always kind of good, and this is if you want to drag your pole, your root locus curves to a certain direction. Always you can use zeros because they're going to end in that 0, right? Yeah. Still important to know what poles and zeros are doing in your system, and this is where we are trying to get that. In practice, if you go out and design controllers, you will probably most of the time do it with MATLAB, but still it's important to understand where this whole thing comes from, right? Okay, this is basically what I said, and really I think this is what I'm not sure, I added this statement on the weekend one more time. The whole methodology of root locus is really not restricted to PID controllers, but a PID controller is very powerful because it comes along with 2 zeros and an integrator. So it decently brings speed, fastness, and it gives you the possibility to head for steady state accuracy for step inputs, right? Still, if you want to think of more complicated controllers, the root locus method, especially when you use a MATLAB or other tools, Python, whatever, they are really, you have all the possibilities to plug in even 10 zeros in your controller, but you should realize your life is going to get harder because if you have a controller with 10 zeros, you have to make sure that you can implement the controllers. You will also need to add some parts for the parasitic delay. Okay, that's it for the root locus. Before we finish today's lecture, I want to take a quick look over to our Moodle course because I activated lab exercise number 3, and I really encourage you to do that because lab exercise number 3 actually does the control design for this A300 aircraft we analyzed in lab exercise number 3, and it's not a pure paper calculation. You can do these calculations in parallel using MATLAB, right? So you are supposed to set up all the computations in MATLAB as well, and it basically guides you through it. So to be fair, for the MATLAB part, it's more a tutorial than actually a task, right? So, but still, I want you to learn all these functionalities MATLAB has for the root locus design, and I think this is actually a nice thing. It's bloody slow, this internet today here at the Hochschule. Okay, so make it a little bit bigger. So you have here experiment number 4, and let's open that for a second. So it basically builds up of this aircraft model from exercise numbers. Lab exercise or lab number 3. So you have a transfer function, right, of this aircraft, which is a PDT2 system, and it has a damping of 0.5. And now you should first construct of this system there's an error here. Sorry. The pole 0 map, and then extend it to a root locus plot and so on. And basically it's really just a one-by-one application of all these rules, and to come up with the centroid and the asymptotes and so on, right? It really guides you through, and everything which is in blue you should then check using MATLAB, right? So it really tells you how to implement a transfer function in MATLAB and call the root locus, and you will see it then. Okay. Yeah, same thing here. Then you design the controllers, and then you want to head for steady state accuracy, and you will see that adding the integrator is actually possible in that case, but it's not very good, so you need to add a 0 as well, and so on. So really, yeah, try to do it. If you have questions, don't hesitate to shoot me an email on this, because really for the let's say for the experiments we are doing here, really you can write me emails, because we cannot do it here. For the additional exercises here, I rather would encourage you to come to the office hours. So I actually also activated this guy here, control design root locus examples. Right? So you have a system PD controller, and you want to do now a control design. So there are, I think, 3 examples. Yes, you have the solutions there, and these 3 examples are all constructed in the way that you do the calculations via the geometry. But last semester, one student surprised me actually that you can also obviously solve that problem with different methods. You can just close the loop and calculate the gain, right? But to practice the root locus method, you should try really to solve these 3 problems really with the root locus method, and not by closing the loop and canceling something out and so on, right? So this is also possible, and the result will be the same. You can double check. However, they are intended to actually be done with the root locus design methods. So basically with the angle criterion and with what we just did. Okay, that's basically it from my side. Bye-bye. Thanks for listening.